Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most unsettling and beautiful questions ever asked. Is reality just an illusion? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the nature of reality together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Tonight, we won't be chasing loud conclusions or dramatic revelations. Instead, we'll move slowly through some of the boldest ideas in modern physics and philosophy. Some scientists suggest that the universe we see may be only a surface layer, like the skin of an ocean whose depths we've barely explored. Others wonder whether space and time themselves might be emergent, stitched together from something more fundamental. Perhaps information, perhaps mathematics, perhaps something stranger still. We will explore the simulation hypothesis, which asks whether our universe could be a kind of digital construction. We'll consider the holographic principle, where 3 dimensions might arise from information written on a distant boundary. We will gently examine ideas about hidden dimensions, superfluid spacetime, mathematical structures, and the possibility that what we call reality might be only one branch among many. And then, importantly, we will descend underground, beneath the border of France and Switzerland, to the Large Hadron Collider at CERN, where physicists are not speculating but measuring, where protons are accelerated to energies so immense they approach the speed of light, and where we test whether reality tears, leaks, bends, or remains quietly intact. We will separate what is experimentally supported from what remains philosophical. We will distinguish imagination from evidence, and perhaps, by the end, the question will shift. Not, is reality fake? But something softer and more subtle. What do we even mean by reality in the first place? So settle in. Let your breathing slow. The chair beneath you feels solid. The air feels real. The sound of this voice reaches you through a chain of vibrations and electrical signals that physics can describe with extraordinary precision. And yet, the deeper we look, the less solid everything becomes. Let's begin. If you press your hand against a table right now, it feels firm and unyielding, solid, reliable, the kind of thing you could trust to hold up a stack of books or a cup of tea. Your senses report stability. The world appears continuous, steady, almost reassuringly ordinary. For most of human history, this was enough. Reality was what you could see, touch, and measure with simple tools. The ground was flat beneath your feet. Time moved forward like a river. Space was an empty stage on which matter performed its predictable dance. But over the past century, physics has quietly eroded this comforting simplicity. Let's begin with space itself. You might imagine space as a vast emptiness, a passive container where stars and planets float. But according to Einstein's theory of general relativity, space is not empty and not passive. It bends, it curves, it stretches in the presence of mass and energy. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet dips downward. Now roll a smaller marble nearby. The marble does not move because it is being pulled by an invisible string. It moves because the surface itself is curved. In Einstein's picture, gravity is not a force in the traditional sense, it is geometry. Massive objects reshape the fabric of space and time, and everything else follows those curves. That alone is strange enough. The idea that space can bend like fabric would have sounded absurd to Newton. And yet, we have measured it. We have observed starlight bending around the sun. We have detected gravitational waves, ripples in space-time, from colliding black holes billions of light years away. Already, reality is behaving less like a rigid stage and more like a flexible, responsive structure. Now let's zoom inward to all the tiny scales of atoms. If you picture an atom, you might imagine a miniature solar system, electrons orbiting a central nucleus. But even that picture is too solid. In quantum physics, electrons are not tiny billiard balls, they're excitations in underlying fields. A useful image is a calm lake. When a ripple moves across its surface, we can point to the ripple and say, there it is. But the ripple is not a separate object, it is a pattern in the water. In modern quantum field theory, particles are something like ripples in invisible fields that fill all of space. The electron is not a tiny bead sitting in space. It is a vibration of an electron field that exists everywhere. Even emptiness is not empty. What physicists call the vacuum is not a blank void. It seethes with tiny fluctuations, temporary flickers of energy that appear and vanish. On unimaginably small scales, reality is restless. And then there is time. We experience time as steady and universal. 1 second feels like 1 second everywhere. But relativity tells us that time flows at different rates depending on motion and gravity. A clock placed near a massive object ticks slightly slower than one far away. This is not speculation. It is measured regularly to keep our satellite navigation systems accurate. Your head, very slightly, experiences time faster than your feet because it is farther from Earth's centre of gravity. The difference is tiny, far too small to notice, but it is real. So the world is not flat, not rigid, not empty, not universally timed. And yet, here is the deeper mystery. All of this strangeness is described by mathematics with astonishing precision. Equations written decades ago predicted gravitational waves long before we could detect them. Mathematical structures developed in abstract thought now guide billion-dollar experiments. Why does mathematics fit reality so tightly? Is mathematics merely a language we invented, like musical notation describing a symphony? Or is reality itself somehow mathematical in its core, like the symphony arising from the notes themselves? This is where the quiet question begins to form, not loudly, not dramatically, but gently. If the world we perceive is so different from the world physics describes, then what exactly is real? Is the solid table truly solid, or is it mostly empty space structured by fields and forces? Is space a smooth continuum, or does it have a granular texture at scales so small we cannot yet see them, perhaps around 110 to the minus 35 meters, a distance so tiny it would make an atom look enormous by comparison? Physicists call that scale the Planck length. It is thought to be the smallest meaningful unit of distance in our current theories, a kind of pixel size of the universe, if such a pixel exists at all. We do not yet know. And that uncertainty is not a weakness, it is an invitation. When modern physics unsettles our intuitive picture of reality, it does not immediately imply that reality is fake or illusory, but it does suggest that what we perceive may be only a surface layer, like foam on top of a deeper ocean. So tonight, as we slowly explore simulation hypotheses, holographic universes, hidden dimensions, and the machinery beneath Switzerland that tests these ideas, remember this starting point. We are not questioning reality because it is flimsy. We are questioning it because the deeper we look, the stranger and more structured it becomes. And sometimes the most unsettling discoveries are also the most beautiful. When you say something is real, what do you mean? You might mean that you can touch it. The cool surface of a glass, the weight of a book in your hands, the steady hum of a fan in the corner of the room. Reality, in this everyday sense, is what resists you, what pushes back, what remains when imagination fades. But physics invites a quieter question. Is reality defined by how it feels to us, or by what it is underneath? For most of human history, those two things seemed identical. The world felt solid because it was solid. Time felt universal because it was universal. Objects appeared separate because they were separate. And then, slowly, that alignment began to loosen. Take solidity. The table beneath your hand feels firm. But if you could shrink down to the scale of atoms, you would discover that what appears solid is mostly empty space. Atoms are structured like tiny systems with dense nuclei at their centers and diffuse clouds of probability surrounding them. If the nucleus were the size of a pea placed in the middle of a large cathedral, the electrons would occupy the vast interior space as faint shifting patterns. The rest would be emptiness. And yet you cannot pass your hand through the table. Why? Because what we call solidity is not about packed matter. It is about forces. The electromagnetic interaction between atoms prevents them from overlapping. The table resists you not because it is filled solidly like stone, but because invisible fields enforce boundaries. So is the table real? Yes, but not in the way your senses first suggest. This distinction matters, because already we see that experience and structure are not identical. Experience tells you solid surface. Physics tells you structured fields and mostly space. Now let's widen the lens. Consider colour. A red apple appears vividly red, but redness is not a property floating independently in the apple. It is the result of light of certain wavelengths reflecting from its surface and interacting with receptors in your eyes. Your brain interprets those signals as red. The apple is not intrinsically red in the dark. Redness emerges from interaction. And so again we ask, what is real? The physical wavelength, the neural interpretation, the felt experience? This gentle unravelling does not diminish reality. It deepens it. Philosophers often distinguish between two levels, appearance and ontology. Appearance is how things show themselves. Ontology concerns what fundamentally exists. If reality is defined by appearance alone, then perhaps it is inseparable from perception. But if reality is defined by ontology, by the underlying structure described by physics, then our everyday experience may be only a surface rendering of deeper rules. This idea becomes even more intriguing when we remember how mathematics enters the story. The laws of physics are written in mathematical form. Einstein's field equations relate the curvature of spacetime to energy and momentum. Quantum mechanics describes particles through wave functions and probability amplitudes. Even the behavior of elementary particles can be predicted by equations that look abstract and detached from ordinary life. And yet, when tested, those equations align astonishingly well with experiment. It is as if beneath the world of sensation lies a world of structure that can be expressed in pure relationships. Now imagine two maps. One map is drawn by your senses. It tells you where the ground feels hard, where the air feels warm, where sound echoes in a room. It is vivid and intuitive. The other map is drawn by mathematics. It charts curvature, fields, symmetries, conservation laws. It does not feel warm or cold. It feels precise. Both maps describe the same territory. But which one is reality? Or are they simply two ways of interfacing with the same underlying structure? Some physicists argue that what we experience is a kind of interface, like the icons on a computer screen. The icon of a folder does not resemble the billions of electrical states inside a hard drive. It is a simplified representation that allows you to interact effectively. In this view, everyday reality may be an efficient representation of something deeper and less intuitive. This does not mean the deeper layer is more real in a dismissive sense. It simply means that our senses evolve for survival, not for revealing ultimate structure. We see what helps us navigate. We feel what helps us respond. The laws of physics, however, aim at something else. They attempt to uncover invariant structures, patterns that hold regardless of perspective. For example, the speed of light in vacuum is constant. No matter how fast you move, light travels at approximately 300,000 kilometers per second. That invariance forces time and space themselves to adjust. Clocks slow, lengths contract. These are not illusions. They are measurable consequences of a deeper rule. So again, reality presents two faces. One face is experiential, warm, textured, immediate. The other is structural, geometric, relational, mathematical. When people ask whether reality is an illusion, they often mean, is what we perceive merely a projection? But perhaps a more careful question is this: is perception the final layer or the interface layer? If what we perceive is an interface, then reality might not be false. It might simply be deeper than it appears. And once that possibility settles gently in the mind, the bold frameworks we will explore, simulation, holography, hidden dimensions, no longer sound like dramatic rejections of reality. They begin to sound like proposals about what lies beneath the interface. Before we leap into those ideas, it is helpful to let this distinction breathe. Reality as experience, reality as structure, two lenses, one world, and somewhere between them, the quiet space where curiosity begins to drift. There is a quiet mystery at the heart of science, one that does not involve black holes or hidden dimensions, but something even stranger. Why does mathematics work so well? Not just reasonably well, not approximately well, but astonishingly, almost uncannily well. The universe seems to follow equations. When Johannes Kepler studied the motion of planets, he found that their orbits were not random. They traced elegant ellipses. Those paths could be described with precise mathematical relationships. Later, Isaac Newton expressed gravity in a compact formula that related mass, distance, and force. With that equation, he could predict how apples fall and how moons orbit planets. Centuries later, Albert Einstein refined gravity again. Instead of force, he described space-time curvature. The mathematics became more abstract, filled with tensors and geometric relationships, and yet those equations predicted phenomena no one had ever seen. For example, gravitational waves. Einstein's equations implied that when massive objects accelerate, they should create ripples in space-time itself, like waves spreading across the surface of a pond. For decades, these waves were only mathematical consequences. No instrument was sensitive enough to detect them. Then, in 2015, detectors observed them. Tiny distortions in space-time from colliding black holes billions of light-years away. The math had quietly been correct for nearly a century. It is moments like that which make physicists pause. Mathematics is not simply helping us organize data. It seems to anticipate nature, even quantum mechanics, which governs the microscopic world, relies entirely on mathematical structures. The behavior of particles is described through wave functions, abstract objects that encode probabilities. These wave functions evolve according to precise mathematical rules. When experiments are performed, the results align with those predictions to extraordinary accuracy. This pattern repeats again and again, equations first, observation later. So we are left with a gentle but profound question. Is mathematics merely a language invented by human minds to describe patterns we observe? Or is mathematics something deeper, something the universe itself embodies? Some thinkers, including physicist Max Tegmark, have suggested that reality is not just described by mathematics, it is mathematics. In this view, the universe is a mathematical structure. Every particle, every field, every galaxy is part of an abstract network of relationships that exist independently of human thought. It is a bold claim. To understand why it arises, consider symmetry. Many physical laws are symmetrical in subtle ways. For example, the laws of physics appear to behave the same today as they did yesterday. They appear to behave the same in one location as in another. These symmetries are not just aesthetic, they correspond to conservation laws. When physics is symmetric in time, energy is conserved. When physics is symmetric in space, momentum is conserved. These connections were formalized in the early 20th century by mathematician Emmy Noether. She demonstrated that every continuous symmetry in the laws of physics corresponds to a conservation principle. That is not poetic metaphor. It is a precise theorem. Symmetry gives birth to conservation. Conservation gives stability to the universe. This intimate relationship between abstract mathematical symmetry and physical behavior is difficult to dismiss as coincidence. And yet, critics caution us. Perhaps mathematics works because we shape it to fit what we observe. After all, mathematics is flexible. We invent new branches of it when old tools prove insufficient. Non-Euclidean geometry was developed long before it was applied to spacetime curvature. Complex numbers were once considered purely imaginary, and now they are indispensable in quantum theory. Maybe mathematics is like clay. We mold it to mirror reality, and then marvel at the resemblance. But even that explanation feels incomplete. The patterns we uncover often turn out to be far more elegant than expected. Equations written on chalkboards predict particles not yet observed. The Higgs boson was predicted decades before its detection in 2012. The mathematics of quantum electrodynamics predicts the magnetic moment of the electron with accuracy to many decimal places. A precision so refined that experiment and theory align almost perfectly. It is as though the universe and mathematics are deeply intertwined. Imagine again the orchestra metaphor. Suppose you hear a symphony. You could describe it emotionally, warm, tense, triumphant. Or you could describe it musically, in terms of harmonics, intervals, rhythm. The emotional experience is real. The harmonic structure is also real. The symphony exists as both. Now imagine discovering that the harmonic relationships predicted notes before they were ever played. That is what physics often feels like, so we arrive at a fork in interpretation. One path says mathematics is a descriptive language, extraordinarily effective, but ultimately a human tool. The other path says mathematics is ontological. It is what reality is made of. If the second path is true, then our universe might be one particular mathematical structure among many possible ones, and that possibility opens the door to ideas like the multiverse at its most speculative level. But before we wander there, let's rest in the question itself. Why does the universe obey clean relationships? Why are constants stable? Why does light travel at a consistent speed in a vacuum, approximately 300,000 kilometers per second, regardless of the observer's motion? If mathematics were arbitrary, such consistency would be surprising. If mathematics were fundamental, such consistency would be expected. This tension does not yet have resolution. What we do know is this. Every time we peel back a layer of physical explanation, we find more structure, not less, more symmetry, more relational depth, more mathematical elegance, and that observation gently prepares us for what comes next. Because if mathematics lies beneath physical phenomena, then perhaps physical phenomena are not the deepest layer of reality at all. Perhaps they are expressions, patterns, projections. And as this thought settles, we begin to approach the radical frameworks that attempt to answer what lies underneath. For now, it is enough to notice the quiet strangeness. The universe behaves as though it is written in a language that predates us. Whether that language is invented or discovered remains an open question. But it is not a trivial one. It may be the hinge upon which our understanding of reality turns. There is a particular idea that has captured the imagination of scientists, philosophers, and late-night thinkers alike. It does not arise directly from equations, nor from particle detectors buried underground. Instead, it emerges from logic and from the steady advance of technology. The idea is simple to state, though unsettling to consider. What if our universe is a simulation, not a metaphorical one, not a poetic one, but an actual computational construct, a digital environment generated by a more advanced civilization? The simulation hypothesis was most clearly articulated by philosopher Nick Bostrom in the early 2000s. His argument was not that we have evidence of being simulated, rather it was probabilistic. He reasoned like this: imagine the technological civilizations continue to develop increasingly powerful computing systems. Over time, they might gain the ability to simulate entire universes in exquisite detail, including conscious beings inside those simulations. If even one advanced civilization were to run vast numbers of such simulations, then the total number of simulated universes could far exceed the number of base physical universes. If that were true, then statistically speaking, it would be more likely for any randomly selected observer, like you or me, to exist inside a simulation rather than in the original physical layer. Notice something important. This is not a physics experiment. It is a philosophical probability argument. No particle accelerator has detected a pixel at the edge of spacetime. No telescope has seen the grid lines of a cosmic rendering engine. The hypothesis rests on reasoning about future capabilities, computational growth, and statistical likelihood. Still, the idea resonates with certain features of modern physics. Consider the way quantum mechanics behaves. At very small scales, particles do not have definite positions until measured. Instead, they are described by probability distributions. Only when an interaction occurs does a specific outcome appear. Some have drawn a parallel between this and computational rendering. In certain video games, distant objects are not fully rendered until the player approaches them. The system conserves resources by calculating detail only when necessary. It is a tempting analogy, but we must be careful. Quantum indeterminacy does not imply digital programming. The mathematics of quantum theory does not require a hidden computer. It describes probabilities emerging from wave functions that evolve smoothly according to well-tested equations. Another feature often cited is the existence of fundamental limits. For example, there appears to be a smallest meaningful scale of length in current theories, around 110 to the minus 35 meters, known as the Planck length. Below this scale, our existing models of physics break down. Some interpret this as evidence of a pixel size of reality, but again, caution is needed. The Planck length is not a measured pixel. It is a theoretical scale derived from combining constants of nature, the speed of light, the gravitational constant and Planck's constant, in a way that produces a length dimension. It marks where quantum gravity effects are expected to become significant. It does not prove spacetime is discrete like a digital grid. The simulation hypothesis also raises deep philosophical questions about free will and ethics. If we are simulated, do our choices matter? Are we conscious entities or merely information patterns? Could the simulation be paused, altered, or terminated? These questions drift into territory where physics has little to say. What physics can say is this: so far, no experimental evidence requires the simulation hypothesis. The laws we measure operate consistently and continuously. No glitches have been detected in the cosmic code. High-energy experiments have not revealed hidden computational artifacts. At facilities like the Large Hadron Collider, protons are accelerated to energies of many trillions of electron volts. Collisions are analysed with extraordinary precision. If spacetime had obvious discretization at accessible scales, we might expect subtle violations of symmetries, such as tiny deviations from Lorentz invariance, the principle that the laws of physics are the same for observers in uniform motion. So far, those symmetries remain intact to remarkable accuracy. This does not disprove simulation. A sufficiently advanced simulation could mimic continuous physics perfectly within the range we can probe, and that is the quiet tension of the hypothesis. It is difficult to test. A simulation that is detailed enough to generate observers capable of questioning. It might also be detailed enough to conceal its own computational nature. So where does that leave us? Perhaps with a softer interpretation. Instead of asking whether reality is literally a computer program, we might ask whether physical laws behave like algorithms. Do they operate as rule-based processes that generate outcomes step by step? In some sense, they do. Equations evolve systems forward in time. Quantum field interactions follow specific transformation rules. Information plays a central role in modern theoretical physics, especially in discussions of black hole entropy and the limits of information storage. But none of this requires an external programmer. It could simply mean that reality has structure, that it follows consistent rules. The simulation hypothesis, then, is less a scientific conclusion and more a philosophical mirror. It reflects our growing awareness that the world is deeply structured, deeply lawful, and perhaps far more abstract than our senses suggest. Whether that abstraction corresponds to computation in some higher realm remains unknown. For now, it is enough to hold the idea gently, not as a declaration that reality is fake, but as one possible way of imagining that what we see may not be the deepest layer. And as we continue, we will encounter a framework that does not rely on advanced civilizations at all, but arises directly from black holes, entropy, and the mathematics of gravity. A framework that suggests our three-dimensional world might itself be encoded on a distant surface. And that idea too carries its own quiet strangeness. There is a different path to questioning reality, one that does not begin with computers or simulated worlds, but with something far more ancient and far more violent: black holes. For decades, black holes were imagined as simple cosmic traps, regions of space where gravity is so strong that nothing, not even light, can escape. At their boundary lies what physicists call the event horizon, a surface beyond which return is impossible. But in the 1970s, something unexpected happened. Physicists began asking a strange thermodynamic question. If you throw information into a black hole, a book, a star, a collection of particles, what happens to the information contained within it? In physics, information is not a poetic term. It refers to the detailed description of a system, the arrangement of particles, their states, their relationships. And according to the laws of quantum mechanics, information should not simply vanish. Yet black holes seem to swallow it entirely. This tension led to an astonishing realization. Jacob Bekenstein proposed that black holes must possess entropy, a measure of disorder or information content, and Stephen Hawking later showed that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. But here is the part that startled physicists. The entropy of a black hole does not scale. With its volume, it scales with the area of its surface. In everyday objects, entropy increases with volume. A larger box can contain more configurations inside it. But for a black hole, the information content appears to be proportional to the area of its event horizon, not the three-dimensional volume enclosed within it. Imagine that. All the information describing everything that falls into a black hole can be encoded on its two-dimensional boundary. This discovery inspired physicists like Gerard Tufte and Leonard Susskind to propose something radical. Perhaps this is not just a property of black holes. Perhaps it is a property of the universe itself. This idea became known as the holographic principle. To understand the metaphor, think of a hologram, the kind sometimes printed on credit cards. A hologram appears three-dimensional, yet all of its information is stored on a two-dimensional surface. The depth you perceive emerges from interference patterns encoded on that surface. The holographic principle suggests something similar about our universe. What if everything inside our three-dimensional space, every galaxy, every particle, every event, could be described entirely by information encoded on a distant two-dimensional boundary? Not that the world is flat, not that depth is fake, but that depth might emerge from more fundamental information written elsewhere. In the late 1990s, this idea gained mathematical support through what is called the anti-de Sitter and conformal field theory correspondence. Rather than speaking in symbols, we can describe it gently. It is a duality, a surprising equivalence between two different types of physical theories. One theory describes gravity in a higher dimensional curved space. The other describes quantum fields without gravity on a lower dimensional boundary, and remarkably, calculations in one framework correspond precisely to calculations in the other. It is as though two different mathematical languages describe the same physics from different vantage points. This does not mean our universe is literally a projection like a movie on a wall. It means that under certain conditions, the physics inside a volume can be fully captured by physics defined on its boundary. Now pause and let that settle. If a three-dimensional world can be equivalent to a two-dimensional description, then dimensionality itself may not be fundamental. Depth might be emergent. Just as temperature emerges from molecular motion and solidity emerges from electromagnetic interactions, perhaps spatial volume emerges from informational structure. This possibility shifts the question of illusion into something subtler. The holographic principle does not say reality is fake. It says reality might be encoded differently than it appears. In fact, the principle preserves physical consistency. It respects quantum mechanics. It arises from attempts to prevent information loss in black holes. It is not a science fiction invention. It grows directly out of efforts to reconcile gravity and quantum theory. And yet, it carries a philosophical echo. If the entire content of a region of space can be described by information on its boundary, then what we experience as inside may not be the deepest layer. It might be relational. Information might be more fundamental than geometry. Some physicists even speculate that space-time itself, the smooth four-dimensional fabric described by general relativity, could emerge from networks of quantum entanglement. In this view, the connectivity between quantum systems gives rise to the geometry we perceive as space, geometry from information, volume from relationships, depth from encoded patterns. Notice how this differs from the simulation hypothesis. The simulation hypothesis imagines an external computational layer generating our world. The holographic principle remains entirely within physics. It does not require a programmer. It does, not posit an external realm of beings. It suggests that our universe may have a dual description, one gravitational and volumetric, the other non-gravitational and surface-based. It is a reorganization of understanding, not a dismissal of reality. Still, it gently destabilizes intuition. If our three-dimensional experience could correspond to a two-dimensional encoding, then perhaps dimensionality is not what it seems. Perhaps the universe is less like a solid block of marble and more like a pattern woven into a surface. As we move forward, we will encounter yet another framework that imagines our universe not as encoded on a surface, but as floating within a higher dimensional space, like a membrane suspended in something larger. And each of these ideas in its own way suggests that what feels fundamental may not be the final layer, not illusion, but emergence, not deception, but depth. So far, we have imagined reality as possibly rendered or perhaps encoded on a distant surface. Now we gently turn to another possibility, one that arises not from philosophy, but from attempts to unify the forces of nature. What if our entire universe is like a membrane? In certain extensions of string theory, the fundamental building blocks of nature are not point-like particles, but tiny vibrating strings. These strings require more dimensions than the familiar three of space and one of time. In some versions of the theory, there may be additional spatial dimensions we do not perceive directly. Within this framework emerges the idea of a brane, short for membrane. A brane is a multi-dimensional surface. Our universe, in this picture, could be a three-dimensional brane embedded in a higher dimensional space, sometimes called the bulk. Imagine a soap bubble floating in a vast invisible atmosphere. Creatures living on the surface of the bubble would experience only 2 dimensions of space along the surface. They might not realize that their entire world curves within a larger 3-dimensional space. Similarly, we might be living on a 3-dimensional brane within a higher dimensional environment we cannot directly access. This idea offers a curious way of thinking about gravity. Among the fundamental forces, electromagnetism, the strong nuclear force, the weak nuclear force, and gravity is astonishingly weak. A small refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. Compared to the other forces, gravity seems diluted. One speculative explanation is that gravity is not confined to our brain in the same way as other forces. While electromagnetism and nuclear forces might be restricted to our 3-dimensional surface, gravity could extend into the higher dimensional bulk. It may leak into extra dimensions, weakening its apparent strength within our universe. This is not established fact. It is a theoretical possibility, but it leads to something testable. If extra dimensions exist and gravity interacts with them, then under extreme conditions, such as very high-energy particle collisions, subtle effects might appear. For example, collisions might produce microscopic black holes that evaporate almost instantly. Or energy might seem to vanish from our detectors because it has slipped into extra dimensions. Experiments at the Large Hadron Collider have searched for such signatures. So far, no evidence of extra dimensions has appeared. No microscopic black holes have been detected. No unexplained energy loss beyond standard expectations has been observed. Still, the search continues. Brain cosmology also offers a different way to imagine the beginning of the universe. Instead of a singular explosion from nothing, some models propose that the Big Bang could have been the result of 2 brains colliding within the higher dimensional bulk. The immense energy of that collision would appear to observers within the brain as an expanding universe. From our perspective, it would look like a cosmic beginning. From a higher dimensional viewpoint, it might resemble 2 surfaces brushing past one another. Again, this is speculative, but it is mathematically structured speculation, not fantasy. It arises from equations attempting to reconcile quantum mechanics and gravity into a single framework. The emotional effect of this idea can be unsettling. If our universe is a brain floating in a higher dimensional space, then our visible cosmos might be only one surface among many. Other brains could exist parallel to ours, separated by distances along dimensions we cannot perceive. But here we must remain grounded. There is no evidence that we can access such brains. No experiments suggest portals or tears in space-time. Popular stories about colliders opening doorways into other universes belong to fiction, not physics. The mathematics of extra dimensions is subtle and constrained. If they exist, they are likely compactified, curled up at scales far smaller than we can directly measure, perhaps near the Planck length, around 110 to the minus 35 meters. That distance is so small that comparing it to everyday objects becomes almost impossible. If an atom were magnified to the size of the observable universe, the Planck length would still be unimaginably tiny within it. These extra dimensions, if real, would not be large corridors waiting to be entered. They would be hidden structures woven into the fabric of reality at scales beyond current reach. And yet the idea carries philosophical weight. Just as the holographic principle challenges our intuition about dimensionality, brain cosmology challenges our sense of isolation. Our universe might not be the totality of existence, but one layer within a broader geometric structure. Notice the pattern emerging across these frameworks. Simulation suggests that our reality may be generated from a deeper computational layer. Holography suggests that our three-dimensional world may be encoded on a two-dimensional boundary. Brain cosmology suggests that our universe may be embedded within higher dimensions. Each idea points to depth. None of them claim that the world is fake. Rather, they propose that what we experience may not be the most fundamental description. Reality in this sense may be layered. As we continue, we will encounter an even stranger thought experiment, one that asks whether the multitude of particles we observe might, in some sense, be manifestations of a single entity tracing a path through space-time. And with each step, the familiar world will not dissolve. It will simply become more intricate, more structured, more mysterious. For now, let the image linger gently in your mind. A vast cosmic membrane, curved and expanding, carrying galaxies like tiny beads along its surface, all while floating within a space we do not yet understand. Not illusion, but architecture, not emptiness, but hidden, dimensions quietly shaping what we see. There is a story, half serious, half playful, told among physicists about the nature of electrons. It begins with an observation so ordinary that we rarely notice it. Every electron in the universe appears identical, not similar, not almost identical. Identical. The electron inside your body has exactly the same mass, the same electric charge, and the same intrinsic properties as an electron in a distant star billions of light years away. If you were to swap them, no experiment could tell the difference. In everyday life, objects vary. No two leaves are perfectly alike. No two fingerprints match. But electrons do not carry individuality. They're indistinguishable in the deepest physical sense. This peculiar uniformity led physicist John Wheeler to propose an idea that is both elegant and strange. What if all electrons are actually the same electron? What if there is only one electron in the universe tracing a vast and intricate path through space-time, appearing to us as many because its trajectory loops forward and backward through time? In the mathematics of quantum electrodynamics, there is a formal symmetry in which an antiparticle, such as a positron, can be interpreted as a particle moving backward in time. Richard Feynman famously visualized particle interactions using diagrams in which a positron is represented as an electron traveling in reverse temporal direction. From this mathematical perspective, it becomes possible, at least conceptually, to imagine a single electron weaving through the four-dimensional fabric of space-time, intersecting our present moment again and again. Each intersection would appear to us as a different electron, like a thread passing repeatedly through the surface of a woven cloth. Each crossing looks separate from above, yet below the surface, it is continuous. It is important to understand what this idea is and what it is not. It is not an established theory. It is not supported by direct experimental evidence. It is a thought experiment, inspired by symmetry and mathematical structure, but it invites a deeper philosophical reflection. When we see many identical particles, are we witnessing many independent entities, or are we observing multiple manifestations of a single underlying structure? The one-electron hypothesis also highlights attention. If every electron is a segment of one long world line, a continuous path through space-time, then we might expect symmetry between electrons and positrons. If positrons are simply electrons moving backward in time, then the number of electrons and positrons should be roughly equal. But observations tell a different story. The universe is dominated by matter rather than antimatter. Electrons vastly outnumber positrons. This imbalance is tied to subtle asymmetries in the laws of physics, phenomena known as charge parity violation, or CP violation, in certain particle interactions. Matter and antimatter do not behave as perfect mirror images. Tiny biases appear. These asymmetries may help explain why the universe contains more matter than antimatter. This empirical fact makes the one-electron idea difficult to reconcile with observed reality. The symmetry required by the hypothesis does not fully match the asymmetry measured in experiments. And yet, even if the literal claim is unlikely, the thought experiment remains powerful. It reminds us that individuality at the particle level may not mean what we intuitively think it means. In quantum mechanics, identical particles are described by wave functions that are either symmetric or antisymmetric under exchange. This mathematical property leads to profound consequences, such as the Pauli exclusion principle, which prevents electrons from occupying identical quantum states. The indistinguishability of particles is not philosophical speculation. It is embedded in the equations of quantum theory and confirmed by countless experiments. So when we look at a cloud of electrons in an atom, we're not observing a collection of labeled beads. We're observing a structured pattern governed by symmetry principles. The one-electron hypothesis simply pushes this idea further. What if multiplicity itself is emergent? What if what appears as many is, at a deeper level, one? This theme resonates with earlier frameworks. The holographic principle suggests that volume may emerge from surface encoding. Brain cosmology suggests that our universe may emerge from higher dimensional geometry. Now this thought experiment suggests that identity might emerge from a single continuous entity tracing complex paths. Across these ideas, a pattern appears. Reality may not be built from independent, isolated pieces. It may be woven from relationships and continuity. Still, we must remain careful not to drift into mystical overreach. The one-electron universe remains speculative. It faces significant challenges from empirical data. The asymmetry between matter and antimatter, measured in particle accelerators and observed in cosmology, resists such a simple unification. Yet as a conceptual lens, it invites us to reconsider assumptions. When we say there are countless particles in the universe, what do we mean by countless? Are we counting truly separate entities, or are we counting intersections in a deeper structure? In daily life, individuality feels obvious. Each person is distinct. Each object occupies its own place. But at the level of fundamental physics, identity becomes less concrete. Particles lack serial numbers. Fields permeate space uniformly. Symmetry governs behavior. Perhaps multiplicity is not illusion, but perspective. Perhaps many is a way of viewing one from a particular angle in space-time. And as we continue, we will explore another attempt to reconcile unity and multiplicity, one that imagines space-time itself not as rigid and geometric, but as something more fluid, something capable of subtle currents and hidden vortices beneath its smooth surface. For now, let the image linger gently, a single luminous thread looping through time, weaving the fabric of what we perceive as many, not confirmed, not proven, but suggestive. A reminder that even the simplest particle may conceal a story more intricate than it first appears. So far, we have imagined reality as possibly encoded on a surface, embedded in higher dimensions, or even woven from a single continuous thread. Now we turn to something more tactile, though still deeply theoretical. What if space-time is not rigid at all? What if it behaves more like a fluid? To understand why physicists would consider such a possibility, we need to recall a central tension in modern science. On large scales, planets, stars, galaxies, gravity is described by general relativity. In this framework, space-time is smooth and continuous. It bends and curves in response to mass and energy. It behaves like an elegant geometric fabric. On extremely small scales, atoms and subatomic particles, the world is governed by quantum mechanics. Here, fluctuations dominate. Uncertainty is built into the structure of theory. Fields vibrate, particles appear and disappear. These two descriptions are both extraordinarily successful in their respective domains, yet they resist unification. When physicists attempt to describe gravity using quantum principles in the same way as other forces, infinities appear in the equations. The mathematics becomes unstable. This suggests that something is missing. One approach to resolving this tension is to imagine that space-time itself is not fundamental but emergent, arising from a deeper microscopic structure. Here is where the analogy of a superfluid enters. A superfluid is a state of matter observed in certain substances, such as helium cooled to temperatures near absolute zero. In this state, the fluid flows with zero viscosity. It can climb the walls of its container. It forms quantized vortices, tiny whirlpools that have discrete amounts of circulation. At large scales, a superfluid appears smooth and continuous, but at very small scales, it reveals structured behavior tied to quantum rules. Some physicists have wondered whether space-time might be similar. Perhaps at macroscopic scales, space-time appears smooth and geometric, as general relativity describes. But at extremely small scales, perhaps near the Planck length, around 110 to the minus 35 meters, space-time might possess a granular or fluid-like structure governed by quantum principles. In this picture, gravity could emerge as a large-scale behavior of this underlying space-time fluid, much as sound waves emerge from the collective motion of molecules in air. You do not see individual air molecules when you hear a tone. You perceive the wave. Likewise, curvature of space-time might be a collective effect, not a fundamental building block. This idea connects to laboratory analogies. Physicists have studied certain fluid systems to mimic aspects of black hole behavior. For example, sound waves trapped in flowing fluids can create regions analogous to event horizons. These are sometimes called acoustic black holes. They do not bend light, but they replicate certain mathematical features of gravitational systems. These experiments do not prove that space-time is a fluid, but they show that fluid systems can reproduce behaviors that resemble gravity under certain conditions. This strengthens the conceptual bridge. Another reason this analogy is appealing lies in the way superfluids exhibit quantized vortices. Instead of arbitrary whirlpools, circulation occurs in discrete amounts determined by quantum rules. If spacetime were superfluid-like, then perhaps its microscopic structure would also be quantized. Instead of continuous divisibility, there might be minimal units, subtle grains beneath apparent smoothness. This returns us to the Planck scale. When we combine the speed of light, the gravitational constant and Planck's constant, three fundamental numbers of nature, we obtain characteristic scales of length and time. The Planck length, approximately 110 to the minus 35 meters, and the Planck time, approximately 110 to the minus 43 seconds, represent scales where quantum gravitational effects are expected to dominate. These values are not measured directly as tiny bricks of space and time. They arise from dimensional analysis, from blending the constants that govern relativity and quantum mechanics. Still, they hint that spacetime may not be infinitely smooth. Now imagine the surface of a calm lake. From afar it looks perfectly flat. But if you move closer, you see ripples. Closer still, you see the molecular structure of water. Perhaps spacetime is similar. From astronomical distances, it appears smooth and continuous. But near the Planck scale, it might reveal structure, fluctuations, vortices, patterns of entanglement. Some theoretical models suggest that spacetime geometry may arise from quantum entanglement itself. The connectivity between quantum states could generate what we interpret as spatial distance. In such models, space is not a container. It is a manifestation of relationships. Notice how this differs from the simulation idea. The simulation hypothesis imagines an external computational substrate generating our world. Superfluid spacetime models remain internal to physics. They propose that gravity and geometry emerge from deeper quantum dynamics, not illusion, but emergence, not deception, but layered behavior. There is something almost poetic about this possibility. The smooth curves of spacetime described by Einstein may be the visible expression of invisible microscopic motion. Just as the surface of an ocean conceals currents below, spacetime may conceal its own quantum currents. Yet we must remain grounded. At present, there is no direct experimental evidence that spacetime is literally a superfluid. The idea is exploratory, a conceptual tool to help bridge two powerful theories. But it highlights an important shift in perspective. Instead of asking whether reality is fake, physicists increasingly ask whether what appears fundamental might itself emerge from deeper patterns. Across simulation, holography, brains, and now superfluid analogies, the recurring theme is depth. Reality may not dissolve when examined closely. It may simply reveal layers that are mathematical, relational, perhaps fluid-like in their microscopic behavior. And as we move forward, we will explore a framework that pushes this layering even further, suggesting that not only spacetime but entire universes may exist in parallel configurations shaped by initial conditions and quantum branching. For now, imagine spacetime not as rigid scaffolding but as a subtle medium, quiet, structured, and perhaps gently flowing beneath the stars. By now, a quiet pattern has begun to form. Again and again, when physicists look deeper, they do not find chaos. They find structure, they find symmetry, they find relationships that can be expressed with astonishing precision in mathematical language. This recurring pattern leads to one of the boldest proposals in modern theoretical thought. What if reality is not merely described by mathematics? What if it is mathematics? This idea, most prominently associated with physicist Max Tegmark, is known as the mathematical universe hypothesis. To approach it gently, let us begin with something familiar. Imagine a triangle drawn on paper. its angles sum to 180 degrees in ordinary flat geometry. That statement is not dependent on the material of the paper. It does not depend on ink or pencil. It is a property of the mathematical structure called Euclidean space. Mathematical truths do not decay with time. They do not depend on physical location. They exist in some sense independently of the universe that describes them. Now consider the laws of physics. The motion of planets follows precise mathematical curves. The behavior of electromagnetic fields can be captured by equations. The evolution of quantum systems is governed by wave equations that predict probabilities with extraordinary accuracy. Again and again, the universe seems to behave as though it is instantiating mathematical relationships. This invites a subtle question. Are we discovering mathematics in nature? Or is nature itself a mathematical object? Tegmark suggests that the distinction may be artificial. In his view, a mathematical structure does not merely describe a universe. It is a universe. If a mathematical structure is internally consistent, meaning its rules do not contradict themselves, then it has existence in the same way our universe does. This leads to a striking conclusion. There may not be only one universe. There may be every possible universe that can be defined by consistent mathematics. In this view, our cosmos is simply one particular solution among countless mathematical possibilities. But before this idea drifts too far into abstraction, let us slow down. Why would anyone consider such a radical position? Part of the motivation comes from the remarkable success of mathematical prediction. Take the Higgs boson. Its existence was predicted from symmetry principles in the 1960s. The equations of the Standard Model required a mechanism by which certain particles acquire mass. The Higgs field provided that mechanism, and the associated particle, the Higgs boson, followed inevitably from the mathematics. For decades, no experiment had confirmed it, yet the equation stood firm. In 2012, the Large Hadron Collider detected a particle consistent with the predicted properties of the Higgs boson. The mathematics had not merely described what was known, it had anticipated what was unseen. Or consider the magnetic moment of the electron, a property describing how it responds to magnetic fields. The theoretical prediction and experimental measurement agree to many decimal places. The match is so precise that it feels less like approximation and more like identity. When mathematics predicts physical behavior with such fidelity, it tempts us to believe that physical behavior is itself mathematical at its core. Yet there are counter-arguments. Mathematics is a vast landscape of possible structures. Only a tiny fraction of those structures appear to correspond to physical reality. Why this particular structure? Why these constants? Why this arrangement? Some argue that mathematics is a descriptive tool, refined and expanded to fit observations. We invent mathematical frameworks when needed. We discard those that fail. Over time, the mathematics that survives appears miraculously effective, but only because we have shaped it to mirror nature. This perspective suggests that mathematics is flexible clay rather than fundamental bedrock. There is also the question of meaning. A mathematical structure can exist abstractly, but does it possess physical existence without something to instantiate it? A set of equations describing a possible universe does not automatically create stars and galaxies. The step from abstract consistency to physical reality is not trivial. Still, the mathematical universe hypothesis carries an elegant simplicity. If mathematics is fundamental, then there is no need to explain why mathematical laws describe reality. They describe it because they are it. In this view, physical objects are not separate from mathematical relationships. They are nodes within a network of structure. Mass is a parameter. Charge is a parameter. Spacetime curvature is a geometric property. Everything reduces to relations within a formal system. This idea connects naturally to the concept of a multiverse. If all mathematically consistent structures exist, then there may be universes with different numbers of dimensions. Universes where physical constants differ. Universes where geometry behaves in unfamiliar ways. Our universe would then be one example within a grand mathematical ensemble, yet caution remains essential. The mathematical universe hypothesis is not experimentally verified. It is a metaphysical extrapolation from the success of mathematics in physics. No collider experiment can directly test whether mathematical structures possess independent existence. What we can say is more modest. The universe exhibits mathematical regularity. Symmetry gives rise to conservation laws. Equations predict phenomena not yet observed. Relationships remain stable across time and space. Whether that regularity implies identity with mathematics itself remains open. But as we gently move forward, notice how each framework we have explored shifts the center of gravity away from surface appearance. Simulation suggests deeper computation. Holography suggests deeper encoding. Brains suggest deeper geometry. Superfluid spacetime suggests deeper dynamics. And the mathematical universe suggests deeper abstraction. Across all these ideas, the surface of experience appears less like the final layer and more like an emergent expression of underlying structure. Reality does not vanish under scrutiny. It becomes more relational, more patterned, perhaps even more beautiful. As we continue, we will widen our view further still, exploring how multiple universes might arise naturally from cosmology and quantum mechanics without invoking external programmers or infinite abstractions. For now, let the possibility rest softly in your mind that what we call the physical world may be one particular melody within a vast and silent mathematical symphony. When you look up at the night sky, what you see feels immense. Stars, scattered across darkness. A faint river of light marking the Milky Way. Perhaps a distant galaxy captured by a telescope. And yet, everything you can possibly observe, every star, every galaxy, every photon that has ever reached Earth, lies within what cosmologists call the observable universe. This observable region is not the entire universe. It is simply the portion from which light has had enough time to reach us since the beginning of cosmic expansion. Light travels at a finite speed, about 300,000 kilometers per second. The universe has been expanding for roughly 13.8 billion years. That means there is a limit to how far information can travel to us. Beyond a certain boundary, light simply has not had time to arrive. This boundary is often called the cosmic horizon. Now imagine standing on a vast plain wrapped in thick fog. You can see only as far as the mist allows. Beyond that distance, the landscape continues. Hills, rivers, perhaps entire cities, but they remain hidden from your sight. The observable universe may be like that. Level 1. Multiverse ideas do not require exotic physics. They arise from the simple assumption that space extends beyond what we can see. If the universe is spatially infinite, or even just vastly larger than our horizon, then regions beyond our view likely exist. In those distant regions, the same physical laws apply. The same constants govern behavior. The same types of particles exist. But the arrangement of matter could differ. In one region, galaxies may cluster differently. In another, stars may form earlier or later. Given enough space, every physically allowed arrangement of matter consistent with the laws of physics could eventually occur. This is not science fiction. It follows from statistical reasoning applied to an enormous cosmos. If the deck of cards is shuffled enough times across infinite tables, every possible order will appear somewhere. In that sense level, One multiverse is less about parallel universes in another dimension, and more about distant regions of the same universe. Still, the emotional implication is profound. There may be regions of space unimaginably far away where matter is arranged in configurations nearly identical to ours, perhaps even replicating patterns that resemble Earth. We cannot observe them, we cannot travel there, but within the framework of cosmology, their existence is not forbidden. Now let us move one step deeper. Level 2 multiverse ideas emerge from inflation, a theory developed to explain why the universe appears so uniform on large scales. In the earliest moments after the Big Bang, the universe appears to have undergone an extremely rapid expansion. In a tiny fraction of a second, far less than the blink of an eye, space itself expanded exponentially. Regions that were once microscopic became macroscopic. Inflation explains why distant parts of the observable universe share similar temperatures and properties. It smooths out irregularities like stretching dough until lumps disappear. But certain models of inflation suggest something more. Inflation may not have stopped everywhere at once. In some regions, it may have ended, giving rise to universes like ours, expanding more slowly, forming stars and galaxies. In other regions, inflation may have continued, spawning new pockets of space in an ongoing process sometimes described as eternal inflation. Imagine a pot of water beginning to boil. Bubbles form at different locations. Each bubble expands, separate from the others, even as the surrounding water continues its motion. In inflationary cosmology, each bubble could represent a distinct universe, a region where inflation has ended and conventional expansion begins. Here is where things become especially intriguing. The physical constants in each bubble universe might differ. The strength of fundamental forces, the masses of elementary particles, the number of spatial dimensions. In our universe, the gravitational constant has a particular value. The electromagnetic interaction has a particular strength. The electron has a particular mass, but in other inflationary bubbles those values might be slightly different. If the constants were drastically different, stars might not form, chemistry might not function, life as we know it might be impossible. This possibility connects to what is sometimes called the anthropic principle, the observation that we find ourselves in a universe compatible with our existence, because only such universes can host observers. This does not mean the universe was designed for us. It may simply mean that among many possible variations, we naturally observe the one where conditions allow complexity. Again, caution is important. Inflation itself has strong observational support. Measurements of the cosmic microwave background radiation, the faint afterglow of the early universe, match inflationary predictions with remarkable precision. But eternal inflation and bubble universes remain theoretical extrapolations. They arise from certain versions of inflationary models, not from direct observation of other universes. So where does this leave us? Level 1 multiverse extends our universe beyond our horizon. Same laws, different arrangements. Level 2 multiverse extends variation deeper, potentially different constants, different physical properties. Neither requires portals, neither requires interaction between universes. They arise from cosmological models attempting to explain large-scale structure and early expansion. In both cases, reality becomes less singular, not fragmented, but expansive. Our observable cosmos may be one island within a vast archipelago of space, or one bubble within a larger sea of inflationary expansion. And yet, everything we directly measure, every atom, every photon, every gravitational wave, obeys consistent laws within our region. The multiverse does not erase reality. It enlarges the stage. As we continue, we will descend from cosmic scales to quantum scales, where multiplicity appears in an entirely different form, not through distant space, but through branching possibilities within the fabric of quantum events. For now, imagine standing at the edge of the observable horizon, knowing that beyond the faint glow of distant galaxies, space may stretch far further than light has yet revealed. Not illusion, but immensity, and perhaps more possibility than a single visible sky can contain. Until now, our journey through multiplicity has remained cosmic, distant regions beyond our horizon, expanding bubbles in primordial inflation. Now we gently turn inward, not toward distant galaxies, but toward the smaller scales of reality, the quantum world. In quantum mechanics, particles are described not by definite positions and trajectories, but by wave functions. A wave function encodes the probabilities of different outcomes. Before measurement, a system may exist in what is called a superposition, a combination of multiple possible states. This idea is often illustrated with a simple thought experiment. Imagine a particle that can travel left or right. According to quantum mechanics, before observation, it does not choose one path. Its wave function includes both possibilities. When a measurement is performed, we observe one outcome. The particle is detected either left or right. But what does that mean? One traditional interpretation suggests that the wave function collapses. The superposition reduces to a single outcome. The many worlds interpretation offers a different perspective. Instead of collapse, the universal wave function continues to evolve smoothly according to the Schrödinger equation, the fundamental equation governing quantum systems. In this view, when a measurement occurs, the universe does not choose a single outcome. Instead, reality branches. In one branch, the particle is detected on the left. In another branch, it is detected on the right. Both outcomes occur, but in separate non-communicating branches of the universal wave function. To picture this gently, imagine a quiet hallway that splits into two corridors. Each corridor continues forward independently. Observers in one corridor are unaware of those in the other. The branching is not dramatic. It does not involve explosions or tearing of space. It is a smooth mathematical unfolding of possibilities. Importantly, this interpretation does not imply that we can jump between worlds. There is no doorway connecting branches. Once decoherence, the process by which quantum systems become entangled with their environments, occurs, the branches evolve independently. Decoherence deserves a brief, calm explanation. When a quantum system interacts with its surroundings, even through something as subtle as scattered photons or air molecules, the delicate superposition of states becomes entangled with the environment. The interference patterns that would reveal superposition become effectively inaccessible. From our perspective, the system appears to have chosen a definite outcome, but according to many worlds, no collapse has occurred. The universal wave function has simply evolved into a superposition of branches, each containing a consistent version of events. Why consider such a radical view? Because the mathematics of quantum mechanics does not include collapse as part of its fundamental equations. The Schrödinger equation describes smooth deterministic evolution. Collapse is introduced as an additional postulate to connect theory with observation. The many worlds interpretation removes collapse and allows the mathematics to operate universally. In that sense, it is not adding something new. It is subtracting an assumption. Still, the philosophical implications are vast. If every quantum possibility is realized in some branch, then reality is not singular at the microscopic level. It is a constantly branching structure, but it is essential to clarify something often misunderstood. The branching does not depend on human decisions. It occurs whenever quantum interactions produce entangled outcomes. This means branching happens constantly at microscopic scales, far beyond conscious awareness. Also, probability retains meaning. From the perspective of an observer within one branch, outcomes appear probabilistic because that observer does not know which branch they will experience. Probability becomes a measure of how amplitudes distribute across branches, not a measure of which single outcome becomes real. Now pause and notice the difference between this and earlier multiverse ideas. Level 1. Multiverse arises from vast spatial extension. Level 2 from inflationary dynamics. Level 3 arises from quantum theory itself. No new dimensions are required. No new cosmic regions beyond the horizon. Multiplicity unfolds within the mathematics already confirmed by experiment. Does this mean that countless versions of you exist? Perhaps in a very specific technical sense, but caution is vital. The differences between branches can be unimaginably small. They may involve microscopic variations that never amplify into noticeable distinctions. And again, there is no communication between branches, no meeting, no crossover. This interpretation does not produce science fiction adventures. It produces a reinterpretation of quantum formalism. Many physicists accept it. Many reject it. The mathematics remains the same either way. What changes is how we understand the meaning of probability and measurement. In the context of our broader question, is reality singular or layered? Many worlds suggest that reality may not collapse into one history. It may unfold into many consistent histories, not because of fantasy, but because the equations allow it. And yet, as before, this remains interpretation. Quantum mechanics is experimentally verified to extraordinary precision. The debate concerns what the mathematics implies about ontology, about what exists. As we move toward the final and most speculative level of multiverse, we will encounter an even broader idea, that not only quantum branches, but entirely different mathematical structures might correspond to real universes. For now, let the image rest gently. A universe that does not choose. A cosmos whose possibilities quietly diverge like paths in a forest, each continuing onward, unaware of the others. Not illusion, but multiplicity emerging from the very rules that govern the smallest ripples of reality. We have travelled far, beyond the observable horizon, beyond inflationary bubbles, beyond quantum branching corridors. Now we arrive at the most abstract and most expansive proposal of all. What if every mathematically consistent structure exists as a universe? This idea is sometimes called the Level 4 multiverse. It extends the mathematical universe hypothesis we discussed earlier to its most radical conclusion. To approach it calmly, imagine a vast library. Not a building of wood and stone, but an abstract library containing every possible book that can be written using a fixed alphabet. Some books would be meaningful, some would be nonsense, some would contain entire histories, others would be random strings of letters. Now, replace books with mathematical structures. Each structure consists of elements and relations that do not contradict themselves. Some describe simple geometries, some describe intricate networks, some resemble the equations of our own universe. Others describe realities with different numbers of dimensions, different constants, perhaps entirely unfamiliar forms of interaction. The Level 4 proposal suggests that if a structure is internally consistent, it has physical existence. Our universe would not be unique in principle. It would be one entry in the infinite library. This idea pushes the question of reality into unfamiliar territory. Up to now, every multiverse level we discussed arose from known physics. Level 1 from spatial extension, Level 2 from inflation, Level 3 from quantum mechanics. Level 4 arises from abstraction itself. It asks, why should only one mathematical structure correspond to reality? If mathematics is fundamental, If physical existence is identical to mathematical structure, then perhaps every consistent structure exists in the same sense. But here we must slow down. This proposal is not experimentally testable. No collider can detect other mathematical structures. No telescope can observe alternate formal systems. It is a philosophical extrapolation. Yet it emerges naturally from a certain line of reasoning. If mathematics does not depend on physical matter to exist, if the statement 2 + 2 = 4 remains true regardless of the universe, then mathematical objects seem to inhabit a realm of abstract existence. The level 4 idea suggests collapsing the distinction between abstract and physical existence. Instead of asking why this universe exists rather than another, it suggests that all exist. We simply find ourselves within one compatible with our form of complexity. This view can feel overwhelming. If every consistent mathematical structure exists, then reality becomes an immense landscape of possibility. Universes with 2 spatial dimensions. Universes where gravity behaves differently. Universes where time does not flow in a single direction. Universes where stable matter cannot form. Most of these would be sterile, devoid of observers. We exist in one where complexity is possible. But notice how different this is from saying reality is an illusion. The level 4 multiverse does not say our universe is fake. It says it is one among many mathematically possible realities. Reality remains real within its structure. Its laws remain consistent. Its constants remain stable. What changes is uniqueness. Now step back and view the arc we have traced in these sessions. Level 1. Regions beyond our cosmic horizon. Same laws, different arrangements. Level 2. Inflationary bubbles with possibly different constants. Level 3. Quantum branching within the same mathematical framework. Level 4. Entirely different mathematical structures. With each step, multiplicity expands, yet in every case, the existence of our experienced world remains intact. We have not erased the table beneath your hand. We have not dissolved gravity or light. We have not reduced atoms to fiction. Instead, we have explored whether what we call reality might be one instance of a broader pattern. The emotional weight of this idea can vary. Some feel awe, some feel vertigo, some feel indifference. But at its core lies a gentle philosophical question. Is reality singular, the only structure that exists? Or is it one pattern among many distinguished not by exclusivity but by compatibility with observers like us? Science cannot yet answer that. The level 4 proposal remains speculative, elegant to some, excessive to others. Still, it serves an important purpose in our journey. It stretches the imagination to its limit, and in doing so, it sharpens the contrast between speculation and experiment. Because as we now turn toward the Large Hadron Collider, toward detectors, data, and precise measurement, we will see where imagination yields to evidence. There is a quiet comfort in that shift. We have wandered through possibility. Now we return to what can be tested. Before we descend underground to the great circular tunnel beneath Europe, let one image linger. A library not of stories, but of structures. Shelves extending without end. Our universe. Not a mistake, not a glitch, but one coherent volume among many. Real within its own binding, structured within its own pages, and perhaps not. Alone in the vast archive of possibility. What that means for the nature of reality is something we will continue to approach carefully, step by step, guided not by speculation alone, but by what experiments reveal. The next movement in our journey brings us from abstraction back to collision, from infinite libraries to protons accelerated nearly to the speed of light, from possibility to measurement. And there, beneath layers of earth and stone, physics asks a quieter, sharper question. What does reality do when we push it to its limits? After wandering through expanding bubbles, branching wave functions, and infinite mathematical libraries, it is time to descend, quite literally, back to Earth. Beneath the border of France and Switzerland lies a circular tunnel about 27 kilometers in circumference. Inside that tunnel sits one of the most sophisticated scientific instruments ever built, the Large Hadron Collider. Its purpose is not to tear open reality, not to summon other universes, not to create apocalyptic black holes. Its purpose is far quieter. It collides protons. Protons are particles found in the nucleus of every atom. They are not fundamental in the deepest sense. They're composed of smaller constituents called quarks, bound together by the strong nuclear force. But they are stable, abundant, and convenient for acceleration. Inside the collider, protons are guided around the circular tunnel by powerful magnets. They travel at speeds extremely close to the speed of light, about 300,000 kilometers per second. At such velocities, their kinetic energy becomes enormous on microscopic scales. To make that energy more intuitive, physicists often describe it in units called electron volts. 1 electron volt is the energy gained by a single electron moving through a tiny electrical potential difference. A tera-electron volt means 1 trillion electron volts. When protons collide at energies of several tera-electron volts, the energy involved is roughly comparable to the kinetic energy of a flying mosquito, but concentrated into a space far smaller than an atomic nucleus. That contrast is striking. A mosquito's motion seems insignificant, yet compressing a similar amount of energy into a subatomic collision creates conditions that have not existed naturally since the earliest moments after the Big Bang. Why do this? Because at extremely high energies, new particles can emerge. According to Einstein's relation between mass and energy, often summarized as energy equals mass multiplied by the speed of light squared, energy can transform into mass. When protons collide with sufficient energy, that energy can materialize as short-lived particles not normally present in everyday conditions. By studying the debris from these collisions, physicists can test the structure of the Standard Model, the theoretical framework describing known fundamental particles and forces, excluding gravity. The detectors surrounding collision points are enormous. They are layered with tracking systems, calorimeters, and magnetic fields designed to record the paths, energies, and identities of particles produced in each event. The process is not dramatic in the cinematic sense. It is statistical and meticulous. Billions of collisions occur. Most produce familiar particles. Physicists sift through vast datasets, searching for subtle deviations, tiny discrepancies that might signal new physics. One of the most celebrated achievements of the Large Hadron Collider was the discovery of the Higgs boson in 2012. The Higgs field is a pervasive field thought to give certain particles their mass. Without it, electrons would be massless, atoms could not form, and chemistry as we know it would not exist. The Higgs boson is the quantum excitation of that field, the ripple that confirms the field's presence. For decades, the Higgs was a prediction, embedded in mathematical equations. Its detection required extraordinary precision. When the signal finally appeared, a subtle excess of events at a particular energy, it confirmed that the mathematical framework of the Standard Model was on remarkably solid ground. That discovery did not reveal hidden dimensions or alternate universes. It reinforced structure. The collider continues to test other aspects of particle physics. It measures how particles decay. It examines rare transformations. It searches for hints of physics beyond the Standard Model, phenomena that current equations cannot explain, such as the nature of dark matter. Now let us address directly some common myths. Could the collider create black holes that swallow the Earth? Theoretically, if extra dimensions exist, high-energy collisions might produce microscopic black holes. But these would be extraordinarily tiny and would evaporate almost instantly through a process similar to Hawking radiation. They would not grow, they would not persist. Moreover, nature itself performs higher energy collisions constantly. Cosmic rays, high-energy particles from space, strike Earth's atmosphere at energies exceeding those achieved in the collider. If dangerous black holes could be produced, they would already have formed naturally long ago. Could the collider tear a hole in space-time? There is no theoretical framework predicting such an outcome under the energies involved. The mathematics governing high-energy interactions remains well-defined and consistent. The Large Hadron Collider is not a portal machine. It is a precision instrument. And that precision matters deeply for our broader question. If reality had obvious cracks, if space-time were discretized at accessible scales, if hidden dimensions revealed themselves easily, if symmetries broke unexpectedly, the collider would likely detect signs. So far, the laws of physics hold firm. Lorentz invariance, the principle that the laws of physics are the same for observers moving at constant velocities, remains intact to high precision. Energy and momentum are conserved in collisions. Particle properties align with predictions. This does not close the door on deeper layers of reality. It narrows the possibilities. It tells us that if hidden structures exist, they are subtle. The collider also embodies something else important: transparency. Data from major discoveries are published. Results are scrutinized by thousands of scientists worldwide. Safety assessments are public. There is no secrecy about portals or cosmic threats, because there are none to hide. As we continue into the next session, we will focus more closely on the Higgs field itself, the quiet field that permeates space and endows particles with mass. But for now, let the image settle. Beneath quiet fields and vineyards, protons circle in darkness. They collide, they reveal, and with each collision, reality answers, not with spectacle, but with structure. When we speak about reality, we often assume mass is simply there. The chair has mass, your body has mass, the earth beneath you has mass. Mass feels obvious. It gives weight, it resists motion, it anchors us to the ground. But in the deeper language of particle physics, mass is not automatic. In the equations that describe fundamental forces, particles initially appear massless. Without a special mechanism, electrons would move at the speed of light. The weak nuclear force would behave very differently. Atoms could not form stable structures. Something must give particles their mass. In the 1960s, several physicists, including Peter Higgs, proposed a solution. They suggested that empty space is not truly empty. Instead, it is permeated by an invisible field, now known as the Higgs field. A field, in physics, is something that has a value at every point in space. Temperature in a room is a field. So is the gravitational field around Earth. The Higgs field fills the entire universe. Unlike many other fields, it does not vanish in empty space. Even in what we call vacuum, the quiet background between stars, the Higgs field has a non-zero value. Now imagine walking through snow. If the snow is shallow and light, you move easily. If it is deep and dense, you move more slowly. Your motion is resisted by interaction with the snow. Particles moving through the Higgs field behave somewhat like that. Some particles interact strongly with the Higgs field. Their motion is hindered and they acquire significant mass. Other particles interact weakly, gaining only a small amount of mass. Photons, the particles of light, do not interact with the Higgs field at all. They remain massless and travel at the speed of light. This interaction is not friction in the everyday sense. It is a property encoded in the mathematical structure of the Standard Model, but the snow analogy helps translate that structure into something intuitive. The Higgs boson is the quantum ripple of the Higgs field, the smallest excitation of that field, just as a photon is an excitation of the electromagnetic field. For decades, the Higgs field was required by theory but had not been directly confirmed. The mathematics of electroweak symmetry, the unified description of electromagnetism and the weak nuclear force, demanded a mechanism to break symmetry and generate mass for certain particles. Without the Higgs mechanism, the equations would predict a world very different from ours. So physicists searched. At the Large Hadron Collider, protons were accelerated and collided at immense energies. When enough energy is concentrated in a collision, it can produce heavy particles that exist only fleetingly before decaying. The Higgs boson is one such particle. It exists for an incredibly short time, far less than a trillionth of a second, before transforming into other particles. Physicists do not see the Higgs directly, they see its decay products. By analysing patterns of particles emerging from billions of collisions, they look for statistical excesses, signals rising above background noise. In 2012, two major experiments at the Collider independently reported evidence of a new particle with properties consistent with the Higgs boson. The energy at which this particle appeared corresponded to about 125 billion electron volts. That number may sound abstract, but what matters is that it matched the expectations derived from decades of theoretical work. The discovery was not dramatic in the way movies portray scientific breakthroughs. There were no explosions of light. Instead, there were plots, graphs with tiny bumps where smooth curves had been expected. But those tiny bumps represented confirmation of a fundamental feature of reality. The Higgs field exists, and because it exists, particles have mass. Now pause and consider what this means for our broader question. If reality were an illusion in the sense of being arbitrary or inconsistent, we would not expect such precise alignment between mathematics and experiment. The Higgs field was not invented to explain data retroactively. It was predicted to preserve internal consistency within a theoretical framework. The equations required it, and nature complied. This deep harmony between abstract reasoning and empirical observation does not prove that reality is purely mathematical, but it strengthens the case that underlying structure governs physical behaviour. The Higgs field also reminds us that what feels obvious at human scale may be subtle. At fundamental scale, mass feels primary. Yet it emerges from interaction. Solid objects feel fixed, yet their stability depends on fields permeating space. Reality, then, is not an illusion in the sense of being unreal. It is layered. At one layer you feel weight and solidity. At another, invisible fields define interaction strengths. At yet another, mathematical symmetries constrain what is possible. Each layer is real within its domain. The Higgs field does not diminish the world. It enriches it. It reveals that even emptiness carries structure. That space itself participates in shaping matter, and it anchors our discussion of speculative ideas in something firmly measured. We can imagine bubble universes and branching wave functions, but here, beneath the Earth, detectors have captured evidence of a field that fills all of space. That field is not metaphor, it is part of the fabric of what exists. In the next movement of our journey, we will examine a subtle asymmetry in the laws of physics, a tiny imbalance between matter and antimatter that may explain why the universe contains stars and planets at all. A small tilt in symmetry, a slight deviation, and from it, an entire cosmos of matter. But for now, let the image settle gently. An invisible field everywhere, particles moving, through it like travellers through snow, mass not as given, but as interaction, reality not as illusion, but as intricate design woven from fields we cannot see, yet constantly inhabit. When we look out at the night sky, we see a universe filled with matter. Stars burn hydrogen into helium, planets orbit, galaxies spin. You are made of atoms, protons, neutrons, electrons, all forms of matter. But according to the equations of particle physics, the early universe should have created matter and antimatter in equal amounts. For every particle there exists an antiparticle, a mirror counterpart with opposite electric charge. The electron has a partner called the positron. The proton has an antiproton. These pairs are produced naturally in high-energy processes. When matter and antimatter meet, they annihilate, converting their mass into energy, often in the form of high-energy photons. Now imagine the early universe. Moments after the Big Bang, temperatures were immense. Energies were high enough that particles and antiparticles were created continuously. In a perfectly symmetric world, equal numbers would have formed. As the universe cooled, they would have annihilated each other almost completely. If that had happened exactly symmetrically, only radiation would remain. No stars, no galaxies, no atoms. Yet matter dominates. There is a small excess of matter over antimatter, a tiny imbalance that allowed some particles to survive annihilation and later assemble into everything we see. This imbalance is not dramatic, it is subtle. For roughly every billion particle-antiparticle pairs, perhaps one extra particle remained. 1 in a billion. That faint asymmetry became the foundation of cosmic structure. The question is, why? Physicists describe part of this asymmetry in terms of something called charge parity symmetry. Charge symmetry refers to exchanging particles with antiparticles. Parity symmetry refers to reflecting, spatial coordinates, like looking in a mirror. If the laws of physics were perfectly symmetric under these transformations, then matter and antimatter would behave as exact mirror images. But experiments have shown that this symmetry is slightly broken. In certain processes involving unstable particles, such as neutral mesons, the rates at which matter transforms differ slightly from the rates at which antimatter transforms. These tiny differences are known as charge parity violation. The term may sound technical, but the idea can be softened. Imagine two dancers performing mirror choreography. In perfect symmetry, every movement matches exactly in reverse. But if one dancer hesitates by a fraction of a second, the symmetry breaks. In particle physics, the hesitation is incredibly small, yet cosmically significant. Experiments at particle accelerators, including those at CERN, have measured these asymmetries carefully. They do not destroy symmetry entirely, they introduce a tilt, a preference subtle but measurable. However, the amount of charge parity violation observed in known processes does not fully explain the enormous matter dominance we see today. It is part of the answer, but not the whole story. This suggests that additional mechanisms, perhaps new physics beyond the standard model, may contribute to the imbalance. And here we reconnect with our earlier exploration. The one-electron thought experiment imagined perfect symmetry between electrons and positrons. But the real universe is not perfectly symmetric. That tiny deviation is what made existence possible. Without it, the universe would be filled with light and little else. Matter and antimatter symmetry is another example of how reality appears orderly, yet not perfectly balanced. Symmetry underlies conservation laws, but broken symmetry gives rise to structure. The Higgs field breaks electroweak symmetry, allowing particles to acquire mass. Charge parity violation breaks matter-antimatter symmetry, allowing matter to persist. Reality, it seems, depends on slight imperfections. If reality were a simple illusion, a projection without internal consistency, Such precise and subtle asymmetries would be difficult to explain. Instead, what we observe is a universe finely structured, where even tiny deviations from symmetry have profound consequences. And these deviations are not speculative. They are measured. Detectors record decay patterns. Statistical analyses reveal slight differences in transformation rates. The data accumulate across experiments, confirming that symmetry is not absolute. This brings us back to a central thread. Across simulation ideas, holographic encoding, brain cosmology, superfluid analogies, and multiverse possibilities, we've asked whether reality might be layered. Here, in the imbalance between matter and antimatter, we see a concrete example of layered structure. At one level, symmetry is elegant and pervasive. At another, its breaking gives rise to complexity. The universe is not chaotic, it is delicately tilted. And that tilt, barely perceptible in equations, determined whether galaxies would form. As we move toward the next part of our journey, we will examine other speculative extensions, hidden dimensions, microscopic black holes, and carefully separate myth from measurement. But before we do, let this thought settle quietly. Every atom in your body exists because, in the earliest moments of cosmic history, symmetry was not perfect. A slight imbalance, a fraction beyond equality. From that fraction emerged everything solid, luminous, and alive. Reality may be subtle, it may be layered, but it is not indifferent. It carries within it tiny asymmetries that shaped the entire visible cosmos. And in that quiet tilt, we glimpse how fragile and how profound the structure of existence truly is. When people hear that protons are accelerated to nearly the speed of light and smashed together underground, imagination often races ahead of physics. Headlines whisper about black holes. Speculation imagines tears in spacetime. Stories speak of portals to other dimensions. But when we slow down, when we examine what the equations actually say, the picture becomes far calmer. Let us begin with microscopic black holes. Some theoretical models that include extra spatial dimensions suggest that gravity might become stronger at very small distances. In such models, extremely high energy collisions could in principle produce tiny black holes. But these would not resemble the massive black holes at the centres of galaxies. They would be subatomic in scale. To picture this, imagine compressing the energy of colliding particles into a region far smaller than a proton. If conditions were right, a minuscule black hole might briefly form. Now here is the crucial point. According to well-established theoretical work by Stephen Hawking, black holes are not perfectly black. They emit radiation due to quantum effects near the event horizon. For microscopic black holes, this radiation would cause them to evaporate almost instantly, in a fraction of a fraction of a fraction of a second. Their lifetime would be so short that they would disappear before interacting significantly with surrounding matter. There is no scenario within mainstream physics in which such a black hole grows uncontrollably. In fact, nature performs higher energy experiments constantly. Cosmic rays, high-energy particles from distant astrophysical sources, collide with Earth's atmosphere at energies exceeding those achieved in particle accelerators. If dangerous black holes could be formed in such collisions, Earth, and every planet and star, would have faced that risk for billions of years. They remain intact. This simple astronomical fact is one of the strongest safety reassurances. Now let us address the idea of tearing dimensions. Some theories, such as those involving extraspatial dimensions beyond the familiar three, arise in attempts to unify gravity with quantum mechanics. In certain string-inspired models, additional dimensions may be compactified, curled up at scales far smaller than atoms. The Large Hadron Collider searches for indirect evidence of such dimensions, perhaps through missing energy signatures or deviations in particle behavior. But detecting evidence of extra dimensions is not the same as opening a doorway into them. Even if extra dimensions exist, they would not behave like cinematic portals. They would be geometric properties of space-time itself, subtle and deeply embedded in the mathematical structure of physical law. No experiment at current energies can rip space-time apart. The equations governing high-energy interactions remain stable and predictive. Physics is not a fragile glass that shatters under inspection. It is more like a woven fabric, resilient, structured, and remarkably consistent. Safety at large research facilities is not treated casually. Before the Large Hadron Collider began operation, extensive safety reviews were conducted by independent scientific panels. Risk assessments were published openly. The reasoning behind them was transparent and publicly available. This openness matters. Particle physics is an international collaboration. Data are shared. Results are peer-reviewed. Discoveries are scrutinized by thousands of researchers worldwide. There are no secret experiments hidden behind closed doors. Science advances through publication, not concealment. And the search continues, not recklessly, but carefully. One proposed experiment, known as SHIP, short for Search for Hidden Particles, aims to explore a different frontier. Instead of focusing solely on high-energy collisions, SHIP would search for extremely weakly interacting particles that might have escaped detection so far. These hypothetical particles could help explain dark matter or other unresolved phenomena. Rather than smashing particles harder, SHIP would listen more quietly, looking for faint traces in controlled environments. Another future project, the Future Circular Collider, envisions an even larger ring than the current collider, extending nearly 100 kilometers in circumference. Such a machine would reach higher energies and greater precision, allowing physicists to test the standard model more stringently and probe for subtle deviations. But even here, the motivation is not spectacle. It is measurement. It is refinement. If hidden layers of reality exist, extra dimensions, unknown particles, deeper symmetries, they will not announce themselves dramatically. They will reveal themselves through tiny inconsistencies, a slight imbalance, a rare decay pattern, a missing fraction of energy that cannot be accounted for. This is how physics uncovers depth, not through rupture, through precision. When myths arise about world-ending black holes or dimension-tearing catastrophes, they often stem from misunderstanding scale. At human scale, energy feels immense. At cosmic scale, the energies we generate are modest. The sun produces more energy in a single second than humanity has generated in its entire history, and the universe remains stable. So where does this leave our broader question? If reality contains hidden layers, additional dimensions, emergent structures, quantum gravitational effects, we're not tearing at them recklessly. We're approaching them gently, with magnets and detectors, with mathematics and patience. If deeper structures exist, they are subtle, and we are looking carefully. No portals have opened, no cracks have formed. But the search continues, not because reality is fragile, but because it is profound. And beneath vineyards and mountains, protons continue to circle quietly in the dark, not to break the world, but to understand it. As our journey has unfolded, we have travelled across immense distances and through delicate quantum scales. We have examined branching possibilities, hidden dimensions, subtle asymmetries, and fields that fill empty space. Now we arrive at a different kind of boundary. Not a cosmic horizon, not an inflationary bubble, not a quantum branch, but a limit of measurement itself. physics is an experimental science. No matter how elegant an equation appears, it must ultimately confront observation. Instruments must measure, data must accumulate, predictions must match results, and yet there are scales so small that our current tools cannot directly probe them. One of these scales is known as the Planck scale. It is defined using three fundamental constants: the speed of light, the gravitational constant, and a quantity called the reduced Planck constant, which governs quantum behavior. When combined in a particular way, these constants define a characteristic length, often called the Planck length. Instead of writing the formula in symbols, let us describe it gently. The Planck length is approximately 1/10,000,000th of a trillionth of a meter. That is, a decimal point followed by 34 zeros before a 1. It is unimaginably small. To compare, an atomic nucleus is about 100,000 times smaller than an atom, and even that nucleus is vastly larger than the Planck length. At this scale, our current theories, general relativity and quantum mechanics, are expected to merge. General relativity describes gravity as the curvature of space-time. It works beautifully for planets, stars, and galaxies. Quantum mechanics describes particles and fields at microscopic scales. It works exquisitely for atoms and subatomic interactions. But at the Planck scale, both gravitational curvature and quantum fluctuations become equally significant. We do not yet possess a fully confirmed theory of quantum gravity, a framework that unifies these two descriptions seamlessly. Various proposals exist. String theory suggests that fundamental particles are not point-like, but tiny vibrating strings. Loop quantum gravity proposes that space-time itself may be quantized, composed of discrete loops or networks. Superfluid spacetime analogies suggest that spacetime might behave like an emergent medium, with smooth, large-scale behavior arising from microscopic structure. But here is the key distinction. These ideas are mathematically developed. Some are elegant, some are internally consistent, yet none have been experimentally confirmed. The energies required to probe the Planck scale directly are far beyond what even the Large Hadron Collider can achieve. To reach such scales would require energies trillions of times greater than our most powerful accelerators. So physicists look indirectly. They search for tiny deviations in particle behavior. They examine gravitational waves. They analyze cosmic microwave background radiation for subtle imprints of early universe physics. So far, all observations remain consistent with established theories within measurable limits. This does not mean deeper layers do not exist. It means they remain beyond current experimental reach, and this is where philosophical caution becomes essential. Untestable does not mean meaningless. Many ideas begin as speculative frameworks and later become testable as technology advances, but untested also does not mean true. There's a difference between mathematical possibility and empirical confirmation. When we ask whether reality is an illusion, a projection, or a layered structure, we must hold that distinction carefully. Some proposals, like the Higgs field, were speculative for decades before confirmation. Others, like certain multiverse levels, may remain permanently beyond direct test. Science does not dismiss speculation outright. It organizes it according to evidence. At present, the Planck scale is a frontier. Imagine trying to measure ripples smaller than ripples themselves. If space-time has grain, if it is not perfectly smooth, that grain may reveal itself only at scales so tiny that light cannot resolve it with current technology. It is like attempting to detect the texture of silk from miles away. You may suspect it has fine threads, but until you bring it close enough, the surface appears smooth. Some physicists suspect that space-time may not be infinitely divisible, that at some scale the concept of continuous distance loses meaning. But again, this is inference. Reality, as far as we can measure, behaves continuously at accessible scales. Quantum discreteness applies to energy levels and certain physical quantities, but space-time itself remains experimentally smooth within current resolution. This restraint is important. It protects us from leaping too quickly from mystery to myth. It keeps speculation grounded. As we approach our final session, the question shifts gently. Not whether reality is fake, not whether we live inside a simulation with hidden glitches, but whether what we perceive as fundamental, space, time, particles, might be emergent from deeper principles we have yet to uncover. The limits of measurement are not walls, they are edges. Edges invite exploration, but they also require patience. Physics grows quiet at the Planck scale, not because reality disappears, but because our instruments whisper rather than shout. And perhaps that quietness is itself instructive. Reality may not be an illusion. It may be layered beyond current reach. But until we measure further, humility remains the most honest companion. In the final movement of our journey, we will gather these threads: simulation hypotheses, holographic encoding, superfluid analogies, multiverse structures, collider precision, and ask once more, calmly and carefully, what do they truly imply, and what remains beautifully unresolved? We began with a simple but unsettling question: is reality an illusion? After travelling through quantum branching, cosmic inflation, invisible fields, subtle asymmetries, interstellar visitors, and the quiet precision of particle accelerators, we return to that question with steadier hands. Let us gather what we've seen. The simulation hypothesis suggests that our universe could be generated by underlying computational processes. If advanced civilizations can simulate conscious beings, and if simulated worlds vastly outnumber base realities, then statistically it becomes plausible that we inhabit one of those simulations. But this remains philosophical reasoning. It offers no measurable anomaly. No glitch has been detected in physical constants. No computational grid has been observed beneath space-time. It is a logical possibility, not an experimental conclusion. The holographic principle proposes that the information describing a three-dimensional region of space might be encoded on a two-dimensional boundary. This idea emerged from black hole thermodynamics, the study of how black holes store entropy. When physicists calculated the entropy of a black hole, they found something surprising. It scales with the surface area of the event horizon, not the volume inside. Entropy, loosely speaking, measures information content. If the information of a black hole scales with area, it suggests that the fundamental degrees of freedom of space-time might reside on boundaries. In certain theoretical frameworks, particularly in anti-de Sitter space, holographic dualities have been mathematically precise. Yet our universe does not perfectly match those simplified models. The holographic principle remains a powerful insight, but not a confirmed description of everyday space-time. Superfluid space-time analogies suggest that space might behave like an emergent medium. Just as water appears continuous but is composed of molecules, space-time might emerge from deeper quantum constituents. This idea is elegant and intuitively appealing, but again, direct evidence is absent. The multiverse proposals, levels 1 through 4, extend possibility in increasing degrees of abstraction. Some arise naturally from inflation and quantum mechanics. Others stretch into philosophical speculation about mathematical existence. Each adds layers, none dissolve reality. And then there is the Large Hadron Collider. Collisions measured to extraordinary precision. The Higgs boson predicted decades before discovery. Symmetry violations recorded carefully. No portals opened. No dimensions torn. Reality, when pressed experimentally, behaves consistently. This does not mean it is simple. It means it is structured. The phrase illusion can mislead. An illusion implies deception, a false appearance hiding nothing beneath. But what we have encountered is not falseness, it is depth. At the human scale, objects feel solid. At the atomic scale, matter is mostly empty space structured by electromagnetic interactions. At the quantum field scale, particles are excitations of underlying fields. At the cosmological scale, space-time curves in response to mass and energy. Each layer refines the previous one. None invalidate it. The chair beneath you is not an illusion because it is composed of atoms. The atoms are not illusions because they are excitations of fields. The fields are not illusions because they arise from deeper symmetries. Reality appears hierarchical, layered, interconnected. We have not found cracks in its foundation. We have found that the foundation extends further than intuition suggests. Perhaps the most honest answer to our question is this: reality may not be fundamental at the level we first perceive it, but it is not unreal. It may be emergent, like temperature emerging from molecular motion, like waves emerging from water. If deeper structures exist, computational, holographic, quantum gravitational, they do not negate the layer we inhabit, they sustain it. And perhaps the word illusion fails because it implies disappearance. What physics reveals instead is continuity. From quarks to galaxies, from fields to forces, from symmetry to structure, the mystery remains. Are we inside a simulation? Possibly, but with no evidence. Is space-time holographically encoded? Perhaps in certain limits. Is reality one universe among many? It could be. Does mathematics describe the universe with uncanny precision? Yes, and that precision is one of the most astonishing facts of existence. But describing something mathematically does not automatically reduce it to abstraction. It reveals pattern. As we rest at the end of this exploration, the question shifts gently. Instead of asking whether reality is an illusion, perhaps we ask, how many layers does it have? And how many remain undiscovered? Science proceeds slowly, patiently, carefully. Speculation stretches imagination. Experiment anchors it. Between those two movements lies curiosity. Reality is not dissolved beneath scrutiny. It has deepened. And perhaps that is more beautiful than illusion. You still feel gravity. You still see light. You still inhabit space and time, but now you carry the awareness that beneath the surface may lie symmetries, information, quantum fluctuations and mathematical structure, all woven together into the fabric of what is. Maybe reality is not a stage set. Maybe it is an ocean. We live on its surface, feeling waves and wind. Physics dives below, mapping currents. Philosophy wonders how deep it goes, and somewhere, at scales too small to measure and distances too vast to reach, structure continues, quietly, consistently, elegantly. Not an illusion, a layered unfolding, and that unfolding, whether singular or one among many, remains the most extraordinary thing we know.